There we go. All right. As we learn more reactions, we're going to develop the ability to make more complicated molecules from less complicated molecules. And one of the best ways to do that is to make carbon-carbon bonds. Notice that I'm giving you a starting material here that was in your practice exam. There are 2 carbons in it, and in the product I've got 4 carbons. So I had to make a carbon-carbon bond somewhere in that process. I'm going to show you a reaction sequence that is summarized in section 8.10 of your text. You may want to go look at that if what I'm going to describe doesn't make a lot of sense. In synthesis problems, depending on their source, if you get them from the text, sometimes they will just tell you, this must be your starting material, this must be your product, use whatever it takes to get from A to B. Other times they'll put constraints on you and say, you have to get from A to B using only whatever reagents. We're going to be sort of open-ended here, and we're going to say you've got to get from A to B using whatever reagents you want and are necessary. So one of the tools in synthesis is going to be for you to look at a complicated product, look at groups in that product, and think, I think I know how I could have made that. I'm going to highlight that by pointing out that these 2 carbons in your starting material are these 2 carbons in your product. Being able to see that and recognize that as a pattern is useful in planning out your synthesis strategy. So your text points out that this starting material is called a vicinal dihalide. That's not necessarily important, other than sometimes you hear people refer to it as such. That comes from, I think, the Latin root for neighbor. Spanish speakers, vecino, right, is neighbor. So vicinal dihalide means a 1,2 dihalide. Halides on neighboring carbons. You'll notice that the 1,2 dihalide looks like it's going to have the opportunity for 2 elimination reactions, because here is the blue alpha carbon that's attached to the blue halide, and there is a neighboring blue beta carbon with a blue beta proton. But similarly, what is our blue alpha carbon is also beta to the orange bromine, right? And so you could imagine doing not 1, but 2 tandem elimination reactions. You would just want a base that is a strong base, but not a good nucleophile. There are many things that work. I will show you one that your text uses a lot. This is a new one on your list of good bases that are poor nucleophiles. It's not one really to memorize, but it is NH2 minus. It will often be written as NaNH2. It's an inorganic salt, and the reason it's not a good nucleophile is because it's not very soluble in organic solvent. But even with those solubility issues, it's a decent base. And so if I add, and now we're going to introduce another term that's useful in synthesis, the idea of equivalence, molar equivalence, or maybe just equivalence for short. This means how many moles of reagent do I add per mole of starting material. So if I have 1 mole of starting material, here I'm going to add 2 molar equivalents, or 2 moles of my strong base. The reason I'm going to do that is because I want to do 2 tandem E2 reactions. I'm going to have 1 equivalent of my base remove the blue beta proton, creating a pi bond, and the leaving group leaves. And my intermediate would be the following, now not vicinal dihalide. The blue bromo group is gone, but the orange bromo group remains and is still anti to the orange beta proton. This intermediate is called a vinyl halide because the halide is on the vinyl carbon. That's not something to memorize, it's just something to recognize as I talk about stuff. Then the second molar equivalent, or the second molecule of NH2 minus, can remove that beta proton and the leaving group leaves. Now, the product there is an alkyne. I want you to notice that that product for you at this stage is unexpected. You've never seen an alkyne product before unless by chance you did the study guide, read chapter 8.10, and then did the practice exam problem. Nevertheless, getting to that alkyne product simply involved two reactions that you know and that are pretty straightforward, okay? Any questions about how we get from the vicinal dihalide to the alkyne product? Yeah. For some reason you thought you couldn't do elimination reactions involving a double bond. Okay, I know where that's coming from. Your text points out that vinyl halides and what are called aryl halides, or halides attached to benzene rings, don't do SN2 or SN1 chemistry. Elimination chemistry is okay. Yeah. There are reasons for why this doesn't happen. We could talk about them, but they're probably not worth our time. They have to do with the fact that, especially with the benzene ring, you can't actually do backside attack. You can't get inside the benzene ring 180 degrees opposite from this bond to attack the sigma star. There are sort of similar steric issues associated with attacking an sp2 hybridized carbon on a vinyl carbon. So that's why it doesn't do SN2, and it doesn't do SN1 because the corresponding carbocations are too unstable. So I think, yeah, that's, but don't over memorize or over apply that. The vinyl halides are okay in elimination reactions. All right, others? So how about getting from the alkyne? I'll write another name for the alkyne, which I'm going to use occasionally. That's acetylene. That's a term that's used for this specific molecule, but it can be used in general for terminal alkynes, that is, alkynes that have at least one CH bond. How about the connection between the alkyne on the acetylene on the left and the desired alkyne product? This is, again, something you may not have considered, though actually I know you've seen something before that gives this as a product. So I'm going to move this down just a little bit. Before, as we introduce the SN2 reaction, we said that this molecule with the alkyne with a negatively charged carbon is both a good nucleophile and a good base. We'll talk about how to get to here from here, but if this is a nucleophile, then what's the other reacting partner? What do you think? What's the electrophile? An alkyl halide, good, and look at the structure of your product. If this is the nucleophile, that then means that in my reaction I need to have made this bond, right? So the other partner needs to have two carbons and a leaving group. So that's simple enough. Here's your two carbons, and then pick your leaving group. It can be bromo, chloro, iodo, don't care, whatever. Let's make it iodo. Then we can make the bond in red simply by the SN2 reaction, and we have no concerns about this because even though our nucleophile is both a good nucleophile and a good base, E2 is slow for primary alkyl halides, whereas SN2 is fast, so it's straightforward to do that. Okay? That's the carbon-carbon bond forming step. That's the step that gets us from something less complicated to something that's more complicated. You're going to want to be really familiar with this type of step because it's the only reaction we know of so far that makes a carbon-carbon bond and builds up something that's more complicated. So in chapters 9 and 10 and 11, when in the back of the chapter they're going to ask you to do synthesis problems, chances are this step is going to be one of them. So I warn you now, it's good to be aware of it. You're likely going to experience it again. Any questions about that? Yeah.
One question on the first step where you're making the alkine.
Yeah.
So I think in the book, they had an example where they had one of the vicinal dialytes in the middle of the long carbon chain.
Yep.
So
that works too.
when it's in the middle of the long carbon chain, what keeps it from just going on to one of the other?
Okay, so one question, yeah, I don't know, is if you had something like this, there are a lot of beta protons, right? And the only ones that give the alkyne product are these ones. What about these ones over here? Do you ever get the single elimination products on either side, I think is your question. I don't have a good answer for that because I've never actually done the experiment in the lab. So I agree with you, I would not be surprised. What we're talking about here is if you try to do this, do you get this product or do you get some mixture of, let's see, 1, 2, 3, of those products? And the answer is, I don't know, this seems pretty reasonable. I can think of an argument why a proton attached to a carbon that already has a bromo on it might be more acidic just because of the inductive effect, and so that may be what controls things. Yeah, I don't know. Yeah, good question. You certainly wouldn't be surprised to see something else, but you can use this reaction as though such issues don't exist. All right, others? Yes?
Back in the other reaction, the synthesis, when did we lose the hydrogen on our acetylide?
Yeah. So when do we lose the hydrogen?
When did we lose the hydrogen?
Yes. Good, that is the missing step. We need something to get us from here to here. And this is going to be a reaction that you learned, you've already said, losing a proton. It's an acid-base reaction. It's something we learned in chapter 2. You simply need a base that is strong enough to remove this proton. And you can look up the pKa of that proton. It's around 25. So you need a base whose conjugate acid is greater than 25. What is most convenient to do, actually, is to use a third molar equivalent of NH2 minus, because, of course, the conjugate acid of NH2 minus is ammonia and has a pKa of 38. So NH2 minus is certainly a strong enough base to remove the proton off of the acetylene. So if I were going to simplify this and write this, delete that. I've written it out sort of stepwise, but if I were in a hurry and trying to make my life easier, I would simply write using 3 molar equivalents of NaNH2, does the 2 E2 eliminations first, then, having formed the alkyne, deprotonates the alkyne to give me this nucleophile. This is the conjugate base of acetylene. It's going to be called acetylide. And then I would just add that electrophile, and that would give me this product. So that's often what people do, is they'll just add 3 equivalents of the base to do the 2 eliminations and the deprotonation all at once. Of course, if you didn't want to make the acetylide, if you wanted to just make the alkyne, you'd use 2 equivalents. That sort of makes sense? Yeah?
Do both the bromides, are those easy reactions, like, are they both coming off at the same time?
Right, do they happen all at the same time? It's probably stepwise, probably it's one and then the other. Yeah. Okay, good. So I think I'm going to punt on biological examples of SN2 and SN1. I really don't want to, but I think in the interests of sanity and moving forward, we probably won't. All right. So now we're going to talk about Chapter 9, which is on alcohols, ethers, and epoxides. But the theme of Chapter 9 is OH minus or OR minus are terrible leaving groups. So what we're going to do, if we want to do SN2 or E2 or SN1 or E1 chemistry with alcohols, our primary concern is going to be turning OH minus into a good leaving group. And again, just to remind you what makes a good leaving group good, a good leaving group is the conjugate base of a strong acid, and that means acids whose pKa's are sort of less than 0. So water's a good leaving group, halides are good leaving groups, OH minus is a terrible, horrible, no good, very bad leaving group. And so we have to have a way to avoid that. So there are many strategies, and we'll talk about them. And but I wanted to just provide a disclaimer at the beginning. Along the way, as we introduce these various strategies, you're going to have a number of questions based on things you've learned before, and sometimes the answers to those questions are either not known or not cared about. So I'm going to try to point out, as we talk about these things that you can figure out on your own versus details you will have to memorize. And I'll provide some tools or suggestions about how to memorize things if that would be helpful. All right, strategy 1 is to convert OH into a good leaving group. You protonate the OH so it can leave as neutral water, which is the conjugate base of a strong acid, right? H3O plus has a pKa of -2. Water is an excellent leaving group. So let's look at this with a primary alcohol. Here is ethanol, 2-carbon alcohol. If we used HCl as our way to protonate the alcohol, what would happen is lone pair electrons on the OH would attack the proton from the acid, thereby turning the OH into a good leaving group. That doesn't look like water, but you should see embedded in this structure is an oxygen bonded to 2 hydrogens, and if it left, it would be neutral water. So having converted water into a good leaving group, now the conjugate base of your HCl acid can come in and do substitution chemistry with your good leaving group alcohol to give you the alkyl chloride. This involves using a halide as a nucleophile. That's something that is new in this chapter. We didn't do any of that in chapters 7 and 8 because halides were leaving groups. When we talked about good nucleophiles, I said that good nucleophiles generally are conjugate bases of acids whose pKa's are greater than 0. The halides are exceptions to that. It has to do with their size and negative charge. Cl- minus is a good nucleophile. It is a poor base. So you can include the halides on the list of things that are good nucleophiles and poor bases. The idea here is that if I had tried to do the reaction just by adding Cl minus alone, nothing would happen because OH minus is a bad leaving group. So I use the acid to first convert to a good leaving group and then have the chloride attack. Yeah?
Does this move in some way into like the protic, aprotic solvents?
Does this move a little bit into protic versus aprotic solvents? There's some stuff in chapters 7 and 8 about how solvent influences nucleophilicity. Yes. we're going to mostly ignore that because it's not necessarily that helpful in us predicting reaction outcomes. But one of the reasons the halides are good nucleophiles, especially in protic solvent, is because they're large enough to escape the cage of solvent molecules that are hydrogen bonding with the negatively charged solvent, or negatively charged nucleophile. Okay, so that's straightforward enough. Protonate, and then what happens with the primary alkyl halide is sort of an SN2 type reaction. It gets a little bit more complicated for secondary and tertiary alcohols. So to illustrate this, I'm just going to show you what the experiments say, and then we'll have to rationalize the data. Here is a chiral alcohol, and it turns out if I use, say, HBr to first protonate the OH group and then have the Br minus attack, instead of SN2 products, what I observe is a mixture of both enantiomers. Okay? If you see that, that tells you that the reaction mechanism was not actually SN2. And so, because we get both enantiomers, it must be SN1. That is, there must be a carbocation intermediate. So we can draw that mechanism and show you how it might have happened. First, lone pair electrons on the alcohol would pick up a proton from the acid, thereby turning what was a poor leaving group into a good leaving group. Again, you need to get used to seeing the water leaving group embedded in that molecule with the positively charged oxygen that's attached to two things. Now, what must happen based on the experimental results, I guess I can slide these over, oops, is that first the leaving group leaves to give a carbocationic intermediate. That intermediate is no longer chiral. We've lost the stereocenter. The LUMO of that intermediate is an empty p orbital. From our perspective, the carbon-carbon and carbon-hydrogen bonds surrounding that positively charged carbon are all in the plane of the page. So the empty p orbital would be coming out toward us and then going back into the plane of the page, evenly spaced on both sides of the carbocationic intermediate, so that in the next step, when Br minus, which is again going to be on our list of things that are good nucleophiles but poor bases, so that when Br minus encounters this carbocation, it can attack either from above or below. And that will give us these two products. All right. Now, here is point number one that is going to be irritating to you. In chapters 7 and 8, as we were dealing with SN1 and E1 reactions, I said that SN1 and E1 basically always compete, right? This is a case where they don't. I don't have a good explanation for why they don't here. If you want a hand-wavy explanation, I can give you one, and it is that Br minus is a really, 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 really terrible base because it's the conjugate base of a really, 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 really strong acid. Nevertheless, you would be right to look at this and say, where are the elimination products? I thought you said there were going to be elimination products. You're right to feel that way. Nevertheless, we're going to follow the text, and we're going to allow you to use this reaction as though there were no competing elimination products. That may be a detail you have to memorize because it's not something you're going to be able to derive from first principles. When you need to memorize a reaction, I recommend doing it in sort of three different ways. It's possible that flashcards are not useful to you. If that's true, feel free to dismiss anything I'm saying. But you might consider memorizing a reaction in a couple of ways. First is you draw the starting material and you draw the reagent, and then you make yourself fill in the blank as to what the products are. Here, your understanding that the products were both enantiomers would help you memorize that the mechanism is SN1. A second flashcard for this reaction would be, here is the starting material, and here are the products, both enantiomers. You have to fill in the reagent. And then the final flashcard, which is actually going to be pretty useful for synthesis, is sort of the thinking backwards flashcard, where you're given the products and perhaps the reagent, and you have to think backwards to the starting material. That may or may not be useful to you, but that's one way you can help yourself remember details that you're not going to be able to derive from first principles. Okay? Yes?
So does the table we built for the previous reaction we were learning not apply here? Because we have like a secondary carbon, but it undergoes SN1 with good profile.
Right. So this does seem to be an exception in more than one way to the chart that you got in chapter 7 and 8. And honestly, it's presented in your text with no such explanation. You're just sort of supposed to accept it. So yeah, recognize that it doesn't fall nicely within the paradigm. Frankly, reality is full of all of these wrinkles. Sometimes things don't go the way we would expect. The chemist learns to look at the results and infer what actually happened. We're going to let reality tell us what happened rather than impose our view of how things should be on reality. Yeah?
So this is the case with any secondary alcohol?
In general, with secondary alcohols, if you use the acids, halides or HCl or HBr, you're going to get a carbocation intermediate. Yeah? Yes?
So would you say make 3 flashcards and have all 3 of those?
So for each reaction, it would be good to, I mean, you can do whatever you want, right? But if you're having trouble memorizing some of these details, thinking through each reaction in these 3 ways is going to be useful to you. Yeah. Okay. It's going to get worse before it gets better. And that is in chapters 7 and 8, when we dealt with carbocation intermediates. We totally ignored something that was going on in the background because we didn't want to deal with it, but we're going to deal with it now. And that is the idea of something called carbocation rearrangement. I wish I had a thing where I could press sound effects, because at that point when I say carbocation rearrangement, we need the psycho violins going, right? Alfred Hitchcock, you guys know what I'm talking about? Maybe not. Go look it up. There's something kind of interesting but also complicated that's been happening in the background anytime we had a carbocation intermediate. So I'm going to introduce this by showing you a slightly different version of the same reaction we just dealt with. It's going to be a secondary alcohol, but the nearby groups are going to be a little bit different. So and we'll just put here, isn't there some painting of some guy screaming like, oh, make it stop, whatever, not funny. And I want you to recognize, well, here are a couple situations where this can occur. And these are the 2 situations that I want you to be aware of. Notice you have your alcohol, hold on. getting ahead of myself. So let's use HCl as the acid. And I'll show you the products of this reaction. They are the following products, some that you would expect. Those are the two products you would expect if you protonate the OH, it leaves, you get a carbocation, and then chloro attacks the positively charged carbon from above or below. And you get the unexpected one, oh, the horror, make it stop. It's terrible. Maybe I'll fill in now. That's fine. I'm not using dashes and wedges on carbons that are not stereocenters, but you should be okay with that. Similarly, we could use HCl here for this reaction, and we would expect to see the following two products. And a third, which is this one. You can tell that something's happened because your leaving group, we turned the OH into a good leaving group. That OH group was at this secondary carbon, but in the product, the nucleophile that came in is on the tertiary carbon, right? So how are we going to explain that? Well, let's start with what we know. Lone pair electrons attack the hydrogen, thereby converting, it into a good leaving group. Again, here is that water embedded as a leaving group in our molecule. And now we've memorized the detail that for secondary alcohols, the water leaving group just leaves. Know that we get sort of SN2 type chemistry. And then here is the carbocationic intermediate. That is a secondary carbon. Not a huge problem, sort of makes sense. If we want these two non-rearranged products, then all we need to do is have our chloronucleophile attack the positively charged carbon. See, I like the arrow to point closer to the carbon than that. So there we go. The positively charged carbon, either from above or below, and that gives us those two non-rearranged products. That's easy so far, that's what we expect. But how do we get the rearranged one? If you look at the intermediate, the positive charge is on the secondary carbon. The adjacent carbon is a quaternary carbon. It has 4 carbons attached to that one carbon. 3 of them are methyl groups. And if you look at the product, one of those 3 methyl groups is now in the wrong place. So that tells you what had to happen. What had to happen here is called carbocation rearrangement. So first, I'm going to draw the arrows for what happens. Then we'll talk through the orbitals. We'll also talk about what this kind of thing is called. So here is one of the methyl groups. I can have that methyl group lean over with its electrons. It sort of picks its electrons up and moves to the other carbon like that. Now that's going to seem bogus because you didn't know you could even do that before. But it's something that can happen. Let's just draw that arrow and then draw the intermediate that would occur if that methyl group picked up with its 2 electrons and hopped over to the adjacent carbon. Now, there are rules for this. This is not just willy-nilly, I'm picking the methyl group up and putting it anywhere. In order for this to happen, there has to be a positive charge on the adjacent carbon, and the methyl group only can go where the positive charge is. Has to be adjacent, right? Because of that, we're going to call this rearrangement a 1,2 methyl shift, because the methyl group was on carbon 1 and now it's on carbon 2. We'll draw, the arrows give you instructions for how to draw the next intermediate. Here's carbon 2. Carbon 2 used to be positively charged. Now it's got the methyl group. This is the one that moved over. On carbon 1, it used to be bonded to 4 things. Now it's only bonded to 3, and so it has a positive charge. That's called a 1,2 methyl shift. It's a carbocation rearrangement. And this can occur anytime you have a carbocation. We're only worrying about it here, though, because it allows us to go from a less stable secondary carbocation to a more stable tertiary carbocation. So that's the driving force for this rearrangement to occur. We can go from something that's less stable to something that's more stable. Okay? And then, now that the positive charge is on the more stable tertiary carbon, the nucleophile can come in and attack. Again, that could happen from either above or below to give you your rearranged product. Okay? So you've got 2 sets of products. You've got not rearranged, and then you have rearranged. For answering questions for me and on my exams, I will want you to show all of these products. Your text is maybe a little bit, I don't know if sloppy is the right word, probably not, but your text sometimes will only show you the rearranged product. On mechanism, on predict products questions, I will want you to show all of them. On a mechanism question, you'll simply need to read the question and see if the question says, draw the mechanism that accounts for the formation of this rearranged product, then do just that. Draw the mechanism that accounts for that rearranged product. All right, questions about the 1,2 methyl shift? Go ahead.
If you were to draw that with wedges and dashes, would you get kind of like a price mixture?
Oh, so if I had drawn, so yeah, it's a good question. If I had used wedges and dashes, would there be stereochemical issues associated here? In this particular problem, no, because all the groups attached here to carbon 1 are identical, so it doesn't matter which one moves over. Second, in the rearranged product, this is not a stereocenter, so you can't actually tell which one moved over. However, there can be stereochemical issues for these rearrangements, and I can show you some examples of that, but none that you'll likely encounter. So we don't know whether, maybe we'll get to it today, but I'll show you some examples where the stereochemistry of the secondary carbocation before the rearrangement impacts the stereochemistry of the carbocation after the rearrangement, but that's not really going to be an issue in any problems you're going to face. Other hands, yeah.
So would the rearranged product be like the dominant product or the more dominant product?
Yeah, it's a good question. Should the rearranged product be the more dominant product over the non-rearranged ones? The story as presented in your text certainly suggests that's the case, though I hedge a little bit because I haven't done these experiments, and frankly, they're not showing you product ratios, so I'd kind of like to see the data myself. Failing that, let's just anticipate all of them. Yeah?
Could you explain why the one on the right is more stable than the one on the left?
The one on the right is more stable than the one on the left because of hyperconjugation. We talked about this as I introduced carbocations in the SN1 reaction. Secondary carbocations are less stable than tertiary carbocations. Do you remember that? The reason for that is the more substituted a carbocation is, the more you have those adjacent CH bonds that can hyperconjugate into the empty p orbital. Okay, others? All right, so now you've got an idea of what can happen below, where the rearrangement came from here. Again, this is going to involve, and I'm going to skip ahead a little bit in the mechanism, but this is going to, the reaction shown here is going to involve an intermediate that looks like this, where you have a secondary carbocation. And again, if you don't do the rearrangement and Cl comes in and acts as a nucleophile, you can get to those products. So this is the unrearranged carbocation. But if we look at that unrearranged carbocation, I'm going to draw it again just so I can do the arrow pushing for the rearrangement. Notice a pattern. You have a secondary carbocation adjacent to, now not a quaternary carbon. Before it was a secondary carbocation adjacent to a quaternary carbon. Here, it's a secondary carbocation adjacent to a tertiary carbon. Here, if the hydrogen takes its electrons and shifts over one atom, that's called a 1,2 hydride shift. It's not a 1,2 proton shift because it's not just the proton that moves over, it's the proton plus 2 electrons, and the name for a proton with 2 electrons is hydride. The 1,2 hydride shift makes it so that, let's see, we need numbers. Here's atom 1, here's atom 2. The hydrogen, the hydride ends up bonded to atom 2, and we have a positive charge on atom 1. As before, we get to go from a less stable secondary carbocation to a much more stable tertiary carbocation. And then, of course, if we do substitution chemistry, that will get us to that rearranged product. Okay. So, yes?
Just a convention, but like why, like if you were naming this compound, you wouldn't call those carbons like the 1 and the 2 carbon?
No, I wouldn't call them 1 and 2. I just did that. I could have called them A and B, or...
But it's like, you still call this a 1,2 hydride?
Right, we call it a 1,2 hydride shift to make it as generic as possible, and that just refers to 2 atoms that are next to each other. Yeah, good. What else? Yeah.
So if you have a longer chain and say the shift happens on like carbons 3 or 4, would you say a 3-4 hydride shift?
If it were longer and the shift happens on carbons 3 or 4, no, you'd still call it 1,2. The 1,2 isn't an absolute, those are not absolute terms, like this is absolutely carbon 1 of my molecule as according to IUPAC rules. That's just terminology that we use in organic chemistry to refer to 2 atoms that are next to each other. It's like alpha and beta. Yeah, go ahead.
Can you just explain how it's a 3' carbon if there's 2 hydrogens and 2 carbons on the right?
The carbocation
Oh, okay.
is tertiary. Yeah. Okay. Good. Now, kind of wonder. I can show you what's going on. Maybe I'll just put this offer out there. If you're okay with the way we've described this 1,2 carbocation rearrangement and you're content with that, that's fine. If you want to know sort of what's going on with the orbitals, I'm happy to show you. You can come to my office and it'll take me just a couple minutes to draw a picture for you. I'm really tempted. I got the picture in my notes and it's really fun for me, but I'm thinking that talking about it is going to be fundamentally self-indulgent because you may not care, you don't want to know, it's an exam day, and you probably don't need to know it to be successful in solving these problems. So what I will tell you is you want to look out, carbocation rearrangements can happen anytime you have a carbocation, but the situations you're going to watch for them are when you have a secondary carbocation that is adjacent to a quaternary carbon or a secondary carbocation that is adjacent to a tertiary carbon. In both of those cases, a 1-2 shift, either of a methyl group or of a hydride, will give you a more stable tertiary carbocation. Those are the situations we're going to worry about it in, okay? Yes?
Can you shift other things that aren't methyl or hydride?
Can you shift other things that are not methyl or hydrides? Yes, and there will be problems, mechanism problems on your study guide and practice exam that require you to do that. If one of these things were not, if one of these carbons attached to either my tertiary or my quaternary carbon were not methyl groups, there could be a rearrangement. I know some of you want to see the worst case scenario, so here's a ring. And here is a secondary carbocation. And yes, you can do a rearrangement where it's not the methyl group that leans over, but is instead this RCH2 group highlighted in pink that simply leans over and makes a new bond. I'm going to try to draw everything in the same way it was drawn. Here is the new bond. Here is the positive charge. 1, 2, 3, 4, 5, 6. We just expanded a 5-membered ring into a 6-membered ring, and then other things can happen. Now, before you withdraw from the class, I will tell you that the only time I want you to predict that a carbocation rearrangement would happen is in the times described here. Secondary carbocation adjacent to a tertiary or quaternary carbon. That's a predict products question. On the other hand, I will want you to be able to consider rearrangements like this on a mechanism question. But the benefit of the mechanism question is that you know the rearrangement happened based on how you see the product. And then as long as you know that rearrangement is in your toolbox, you can get there. Maybe next time I will show you, or maybe the time after that, I don't know, I will show you an example of this kind of thing happening. Well, that's enough for today. Good luck on the exam, and I will see you Friday. See ya.